Okay.
First off, we'll start with ionic. We deal with ions, it's not ironic. Ions, anions, all the time.
All right, let's do this. Let's get these test hints taken care of for Chapter 8, dealing with covalent bonding.
We're done with our shenanigans.
Well, for a while.
Right. Okay, so the first test hint says, the typical characteristics of molecular and ionic compounds. So we're going back even a little bit to Chapter 7, where we started all this bonding stuff, and we did that first lab.
With the little hot plate and the tin foil over the top.
Right, and we melted substances that were ionically bonded and covalently bonded, and we were using that to determine the differences. And then we went right into conductivity, and we used that to help determine the differences between ionic and covalent. So you had your last test where you did a bunch of stuff about ionic, and what did you notice? A lot of those answer choices were things that were about covalent bonding. Well, what do you think is going to happen in this one? We're going to have questions about covalent bonding with answer choices that are ionic. Stop and think about what happens.
Remember which chapter you're in.
Right.
Yes.
Okay, so typical characteristic of an ionic compound would be something that has a very high melting point, soluble in water, definite crystal structure, conducts electricity if it's melted or in dissolved in water. And the covalent ones
have very low melting points, usually liquids or gases. There are some solid ones.
very volatile.
Volatile. The opposite of the ionic bonds.
Right. They're not
That's
really
it.
going to conduct electricity.
Right.
You got some of those acids in between there.
Right.
Okay, so think about what question you're answering. Is it something about ionic or is it something about covalent? Number 2.
It says what a structural formula shows.
Okay,
Well-
see, I don't like these structural formulas.
Well, it's hard to understand the structural formulas if you haven't done the dot structures. And the dashes represent shared pairs of electrons, and the emphasis here is on the trying to show the three-dimensional structure of the molecule,
Right.
trying to show how these atoms are connected without all the clutter
Right.
of everybody's dots.
Right. You know, Mr. Susman, have any of your kids done this? I saw this in my labs.
That's because they can't read molecular formulas yet. They think they're reading H2O
Right.
instead of H2O. They're unsure that the subscript refers to the element immediately preceding
Right.
the subscript.
Right. So don't draw water like that, people.
Yes.
That's not water.
No.
Okay.
Number 3.
What happens to electrons in the formation of a single covalent bond? Now, I gave a checkpoint to my class early on, and they were all telling me about sharing electrons. Sharing electrons? Great. Not good enough. This is about sharing electron pairs. Two electrons, pairs of electrons. Think about how many electrons an orbital can hold. 2. It has to be in pairs. That's what we're worried about.
Right.
Alrighty.
Number 4, the specific noble gas configuration that a specific atom in a molecule obtains. And this ties in with what we were doing in the last chapter, taking a look at filling or satisfying the octet rule. If
Get some water up there for you.
Sure. If oxygen is going to share 2 electron pairs, it's going to have 8 valence electrons. And if you look on the periodic table, sharing 2 valence electrons would give oxygen the exact same electron configuration as neon.
Right. A noble gas. And they're all trying to get to that structure.
Right.
Okay, so it's a question of what does that particular atom have to do? Does it need to share?
Is it sharing 2
one
pairs?
pair, 3 pairs?
Right.
Okay, number 5, the magic 7 and how they bond. Now the magic 7, of course you know, are the elements that start with number 7, nitrogen. They make the shape of a 7 in the upper corner of the periodic table, upper right corner, and there are 7 of them when we include hydrogen, way over on the other side. And these are the elements that we do not find by themselves in nature. They're always running around as pairs. It's going to be H2, N2, O2, F2, Cl2, Br2, I2.
Like girls going to the bathroom at the dance.
In pairs.
Always go in pairs.
You guys don't get that. Okay, so what kind of bond happens between, say, these halogens? These are the halogens. And if we look at their configuration or their electron dot structure, we know that fluorine, oops, let me write that one over there. We know that fluorine has 7 valence electrons, and another fluorine is going to have 7 valence electrons. So when we connect those to show that they're sharing, they are sharing one pair of valence electrons. You need to know halogens by name, you need to know the magic 7, what those elements are, and the fact that they double up.
Number 6. The electron configuration for valence electrons in a hybridized carbon atom.
Hybridized.
This is one of the nerdiest things we did this entire chapter. And these electron configurations, how is this question actually worded?
Well, they want to know about the arrangement, and so what orbitals are going to happen
gotcha.
when, let's say, carbon hybridizes, since that's the most common one.
So you end up with this orbital diagram, 2s2, and then you have 2p here.
This is carbon. This is carbon.
This is regular old carbon.
Minding its own business.
It has 4 valence electrons, but when they hybridize, you end up blending these 4 orbitals together.
Right. Is that like a hybrid plant?
Yeah.
Like, you know, so
Yeah.
at the orchards, they
Yes.
want to make an apple that's prettier and maybe a firmer or better tasting apple, sweeter. They're going to merge 2 different rootstocks together.
What you end up with is 2sp3. Here's the s orbital, and here are these 3p orbitals, and everybody has 1 electron in them.
Okay, so these individual orbitals blend together to make something that chemists in their wild creativity call sp3, because it came from an S and 3 P's.
And 3p's blended together.
And ooh, look what he did with the energy. It's not as low as the s orbital in energy, and it's not as high as the p orbital in energy. It's kind of in between, because you blended it.
Yeah.
Okay, number 7, an example of a simple molecule with a double bond. Well, they made this in their first lab. They made one.
Yeah, my students did it on the first day
Yeah.
of the activity, playing with their Fruit Loops.
Oh,
Yes.
going back to our example of the magic 7, excuse me, darker marker, oxygen is a wonderful example of an atom that can double bond. We have 2 oxygen atoms. They have 6 valence electrons, and I've drawn those in mirror image, and they are going to overlap there.
That's the obvious connection. Everybody should jump on that.
And then they're also going to overlap here. But we don't really draw it that way.
Yeah.
We want to clean it up a little bit, and we know that those unshared pairs are kind of at an angle due to valence shell electron pair repulsion.
The other nerdy thing we did this.
And this isn't the only example of something with a double bond. How about the CO2 molecule?
CO2's got it as well. It has the 2 double bonds going out this way from. Okay. You have carbon, and then you have the oxygen, and of course you're going to jump on this particular bond right there. We have an opportunity to make another bond here. As soon as you realize it, turn your pencil over and slide these guys right back up into the middle. And then the same thing happens on this side, where you have that oxygen, you have, see that? Oops, sorry.
Yeah.
You, 1, 2, 3, 4, 5, 6, count them up. Okay, I got them all. You have this bond. We're going to slide these guys right in. And now we have 2 double bonds headed to the outside away from that central carbon.
Right. Awesome. And that's double bonded. Both of these have a shape that's linear, because I'm sure that's going to come up in one of these questions.
Right.
Because of that double bond, it pulls that flat into one plane.
Mm-hmm.
Alrighty. Number
Where are we? Number 9? Are we on number 9?
right?
Number 9. Number 8. How to identify a molecule made of single bonds from a list of molecules? Well, you can either draw them out,
Or you can count.
or you can count.
Yeah.
That's
Look
exactly
at
right.
how many valence electrons the atom had. If it only needs 1 more, that's the thing that's going to make single bonds. If it needs 2 more, it's going to make a double bond, and 3 more, it's going to make a triple bond.
Right.
Alrighty.
Now
Number 9. The test hint says how a coordinate covalent bond forms. What is it made of? And a coordinate covalent bond shows up a lot in the polyatomic ions. It shows up in some of our trigonal planar things. Go for it.
There you go.
I like the example of ammonia
Yes.
turning into the ammonium polyatomic ion. Okay, so here's the ammonia molecule. Nitrogen has 5 valence electrons. We know that from its column on the periodic table. It had something in following Hund's rule, 1 electron in each available orbital, doubled up with hydrogen's electron and so on. But every once in a while, along comes a bare naked hydrogen atom, the hydrogen nucleus, an H+ ion, in a frenzy. I mean, it's negative after all. And ammonia sees this and says, oh, I happen to have an unshared pair of valence electrons here. Hydrogen, you have no valence electrons. I know you really want 2, so I will be generous and donate both of my electrons to make that bond. That's your coordinate covalent bond. It is the same as a single bond with 2 electrons. It's just that both electrons came from 1 atom.